Welcome back to this next video in which we are discussing quotient rings. Okay, so we're currently in the process of discussing the first isomorphism theorem. Okay, so in preparation for that we have discussed what is meant by the image of a homomorphism. Now what I'll just do is remind you of what is meant by the kernel of a homomorphism, and then we'll state the first isomorphism theorem. Okay, so the kernel of a homomorphism is something that we do go through in a lot more detail in the video on ring homomorphisms and ideals, so I'm not going to go through it in as much detail as I did for the image of a homomorphism, but I will just remind you of what it actually is. Okay, so the kernel of a homomorphism, denoted ker phi, is a subset of the domain ring rather than the codomain ring. Okay, and it's the subset of the domain ring which is all the elements, so all little r is an element of capital R, so all elements of the domain ring, such that the homomorphism maps these elements onto the additive identity in the codomain ring. Okay, so I will underline this in purple here because this is the additive identity in the codomain ring. So it's all elements of the domain ring which are mapped onto the additive identity in the codomain ring. Okay, so drawing a little picture then for this. If we have our domain ring here, and I'll colour that in orange here, like so, and we have our what I will now draw just as the image of the homomorphism. Okay, so I won't bother even drawing the rest of the codomain ring anymore, so I'll just draw the image of the homomorphism here now. Okay, the kernel of the ring homomorphism is a subset of the domain ring, so I'll draw it like so, so it's this subset here, and all the elements that are in this subset are going to be mapped onto one particular element in the codomain ring. They're all going to be mapped onto the additive identity in the codomain ring by the ring homomorphism phi. Okay, so that is what is meant by the kernel of a ring homomorphism. The subset of the domain ring, which is all the elements of the domain ring mapped onto the additive identity in the codomain ring. Okay, right. Now what's important about the kernel of a ring homomorphism is that it is an ideal of the domain ring. Okay, so I can write that the kernel of a ring homomorphism is an ideal of, so I'll use my triangle notation here, of the domain ring capital R. Okay, and then this is something that we do prove in the video on ring homomorphisms and ideals, and I'm not going to go through it again here because it will take me a bit of time, and I'd rather get on to the first isomorphism theorem. So if you're not familiar with that fact, do watch the video on ring homomorphisms and ideals. We go through that. Okay, right. So, that's a reminder then of what the kernel of a ring homomorphism is. Now let's actually state the first isomorphism theorem, which is going to give us a complete understanding of ring homomorphisms. Okay, so the first isomorphism theorem then, I'll just write out its big title here. There are other isomorphism theorems. There are also the second isomorphism theorem and the third isomorphism theorem as well. But the first isomorphism theorem is the most foundational, and that's the one that we're going to go through here. Okay, so the first isomorphism theorem, and if you like you can put of rings, or as it applies to rings, because there is a very analogous theorem for groups that does exactly the same thing but just for groups rather than rings. So you can add the first isomorphism theorem of rings there. Okay, so what does this say then? So this says that the image of a ring homomorphism, and we now know exactly what that is. That's the subring of the codomain ring which actually has elements from the domain ring actually being mapped onto it. This is isomorphic to, and I'll denote isomorphic like so, is isomorphic to the domain ring quotiented out by the ideal, which is the kernel of the ring homomorphism. So I've said that this is an ideal, so we can use it to quotient out the domain ring. And what this theorem says is that if you do so, if you construct the quotient ring of the domain ring by the kernel of the ring homomorphism, you will get an algebraic structure which is the same as the image of the homomorphism up to the fact that you're using different symbols to denote the elements. They are isomorphic to one another. Okay, the job for the rest of this video is to understand why this is true. Okay, so what we're going to do to understand this then is we're firstly going to explore the right-hand side here. We're going to explore what happens if we quotient out the ring by the kernel of the homomorphism, and how does this relate to the image of the homomorphism. And then what we'll do, after we've got a little bit more of an understanding, is we'll write down our precise isomorphism between these two. Okay, so using this picture then here, what does this thing mean here? We are going to quotient out the domain ring, capital R here, by the kernel of the ring homomorphism. So what we're going to do is we're going to partition it up into the cosets of the kernel of the ring homomorphism. Okay, so I'll partition up my domain ring here into the cosets of the kernel of the ring homomorphism, which is this ideal. Okay, and these cosets are now going to become the elements of the quotient ring here, and I can define addition on those cosets and multiplication on those cosets in the way that we have discussed in this video. Okay, now what does that have to do with the image of the homomorphism? So the first thing I want to do is I want to show you that all elements in one of these cosets of the kernel of the homomorphism are mapped by the ring homomorphism onto the same element in the image of the homomorphism. So we know this already for the kernel of the homomorphism. We know all elements of the kernel of the homomorphism are mapped onto a single element, 0 here. So if I like, I could draw some more lines on here. They're all of the elements in here are all going on to that. It's a big convergence potentially here. Okay, and what I want to prove is it's the same for all of these cosets. So if, for instance, I look at this coset here, let's say it contains an element A. So we can call this A bar, the coset that contains A. What I want to show you is that all the elements in this coset containing A bar here, are going to be mapped by the ring homomorphism onto just one element in the image of the homomorphism, and we could call that element phi of A here, okay, because it's the element that A is going to be mapped onto. But we could equally well have called it phi of any one of the other elements in here. They are all mapped onto the exact same element. So I want to prove that all the elements in this coset of the kernel of the homomorphism are going to be mapped onto the same element in the image of the homomorphism. And this is very easy to do, and it gives us a great amount of insight. Okay, so how are we going to do this? Well, we're going to take some arbitrary other element in this coset. And what does an arbitrary other element in the coset look like? Well, it looks like A plus some elements of the ideal, where of course this is addition in our domain ring here. So remember, the way that you construct a coset here is you just take A and you add it to every single element of the kernel of the homomorphism, which is our ideal in this case. So I'm denoting elements of the kernel of the homomorphism by I, and you collect all of those answers together, and that's going to be your coset. Okay, so here is our arbitrary other element of the coset, and what we want to show is that phi will map this arbitrary other element of the coset onto the exact same thing as A was mapped onto. So I want to show that this is equal to phi of A. Now how can I do this? Well, I can just use the fact that this homomorphism, its addition is very compatible with addition in the codomain ring here, so I can split this into phi of A plus phi of the element in the ideal here, where this addition here is now addition in the codomain ring rather than addition in the domain ring. Now, of course, phi of an element in the ideal, we know exactly what that is equal to. That's just the additive identity in the codomain ring here. Okay, because all elements in the ideal, the kernel of the homomorphism in this case, are mapped onto the additive identity. So we've just got phi of A plus the additive identity, and of course this is just equal to phi of A. Okay, so that is why any other element in this coset that contains A will also be mapped onto the same element in the codomain ring as A, so it will be mapped onto phi of A here. Okay, so all elements in a coset of the kernel of the homomorphism are mapped onto the identical element in the image of the homomorphism. That is a great insight, gotten very trivially, I hope you agree. Okay, so very, very easy to prove, but very, very insightful. We now have a good insight into how this is working. Now let's go one step further. Okay, let's prove that elements in different cosets. So let me take another coset here, and let's say this is a coset containing an element called B, so we'll call this coset B bar. So I now want to show that if you've got two elements that are in different cosets, they have to be mapped onto different elements in the image of the homomorphism. So B will go onto a separate element, which we might as well call phi of B, but this is not equal to phi of A. Okay, so I want to prove that elements in distinct cosets of the ring divided out by the kernel of the homomorphism are mapped onto, or rather, in different cosets of the kernel of the homomorphism are mapped onto different elements in the image of the homomorphism by the homomorphism. Okay, so how am I going to do that? Well, I'm going to do it very simply with a proof by contradiction. So I'm going to assume the exact opposite of what I want to prove. I'm going to assume that phi of A is equal to phi of B. So let's just put this here. So I'm going to assume phi of A is equal to phi of B. And from this, I am going to prove that A and B are in the same coset. Okay, that will obviously be a contradiction because I assumed initially they were in distinct cosets. Okay, so how can I do this? Well, the way I can do it is just add on to both sides phi of negative B. So B is some element of the domain ring, it will have an additive inverse which we'll call negative B. So I add on to both sides of this equation phi of negative B, and of course this is addition done in the codomain ring here. So I've added on to this side phi of negative B, I've added on to this side phi of negative B. Perfectly valid algebraic operation. If the initial equation was true, then this modified equation is still going to be true. But now, of course, what I can do is I can use additive compatibility here of the homomorphism to combine this into phi of A plus negative B is equal to phi of B plus negative B, where this addition here is addition in the domain ring. Okay, now, look at this side here, B plus negative B, that's going to give us the additive identity in our domain ring just by definition. B was negative B's additive inverse and vice versa, so those two are going to add together to give the additive identity in the domain ring here. So then when we consider what is phi of the additive identity, well of course that's just going to be the additive identity in the codomain ring. So we get therefore that phi of A plus negative B here is equal to the additive identity in the codomain ring. And therefore, what can we conclude about A plus negative B? We can conclude that it's in the kernel of the homomorphism. Okay? Because that's the definition of things being in the kernel of the homomorphism, that they are mapped onto the additive identity in the codomain ring by the ring homomorphism. Okay, so I can conclude that A plus negative B is an element of the kernel of the homomorphism, where this addition here is done in the domain ring. Okay, now, so it's going to be some element of the ideal, so I'm going to denote that little I. Okay, so if it's in the kernel of the homomorphism, it is equal to some ideal, and I'll just denote that element, it's equal to some element of this ideal, and I'll just denote that element little I here. Okay, perfectly valid to do that. And now what I can do is add B onto both sides, okay, which overall has the effect of taking this negative B onto the other side. Okay, so when I add B onto both sides, it will cancel off this side, and we'll just end up with A on this side, and we'll end up with that it's equal to the element of the kernel of the homomorphism plus B. Okay, and there's my contradiction, because that now means that A and B are going to be in the same coset, because if you like, I can just apply commutativity of addition here and turn this into B plus I, and remember this addition is addition in the domain ring here, so I could still colour all of this in orange here. Okay, so now I've got an equation here that shows quite clearly that A is going to be an element of the coset of the kernel of the homomorphism that contains B. So clearly A is going to be an element of B bar. So that's not good, because I initially assumed that A and B were in different cosets. So overall, what I have done there is I've said, okay, assume the exact opposite of what we want to prove is true, and then I've proven that A and B have to be in the same coset. So I've now proven that if A and B are in distinct cosets of the kernel of the homomorphism in the domain ring, then they must be mapped by the ring homomorphism onto distinct elements in the codomain ring here. Okay, so A and B cannot be mapped onto the same thing in the codomain ring. Okay, so far what we've proven then is that elements that are in the same coset are mapped onto the same element in the image of the homomorphism by the ring homomorphism, and elements that are in different cosets of the kernel of the homomorphism are mapped onto different elements in the image of the homomorphism. Okay, so we have a beautiful correspondence, hence, between elements in the image of the homomorphism and cosets of the kernel of the homomorphism in the domain ring. Okay, and this now is going to become our isomorphism. Okay, so the way that I'm going to find an isomorphism, so remember, to show that the image of the homomorphism is isomorphic to this quotient ring of R by the kernel of the homomorphism, what I have to do is find you an isomorphism between the two, a mapping that will relabel up the elements of one with the elements of the other, and which preserves addition and multiplication. Okay, so I'm going to call this mapping F, and it's going to go from the quotient ring, so from the domain ring quotiented out by the kernel of the homomorphism to the image of the homomorphism. Okay, so this is going to be my isomorphism, and it needs to be a bijective map which preserves addition and multiplication. And hopefully you should be able to guess what I'm now going to use to produce this map. Okay, so it's going to take any coset, so remember the elements of the quotient group are, sorry, not quotient group, quotient ring are cosets, so it will take a coset A bar here, and it will quite simply map it onto the element in the image of the homomorphism which all the elements of that coset are mapped onto. So remember, all the elements of a coset are mapped by the ring homomorphism onto the same element in the image of the homomorphism. So we're going to map this coset onto that element. So what can we use to denote that element? Well, what you'll need to do is take a representative from here. Okay, we might as well take A, and then just take phi of A. So we're going to map a coset onto the element in the image of the homomorphism where all the elements of that coset in the domain ring are mapped onto by the initial ring homomorphism. Okay, so that is how I'm going to define this map. And all that is left to now explain is that this is a bijective map, and that it does preserve addition and multiplication, and hence that it is an isomorphism. So let's firstly take bijective. Okay, so how can I show that this map is bijective? Well, really, I have already stated it, but I'll make it absolutely explicit. So let's firstly start off with it being well-defined. Is it well-defined? Is the one and only one answer for where every single coset in the quotient ring is going to be sent in the image of the homomorphism? Well, the answer is yes, and this is what shows that the answer is yes. All the elements in the same coset are mapped onto the same element in the image of the homomorphism. So it really does not matter which representative you use from the coset to decide which element in the image of the homomorphism the coset is going to be mapped onto. The answer will always be the same. So well defined, we can put a tick next to that. Bijective next. Okay, so we need to make sure it's surjective and injective. Let's start off with surjective. Why is it going to be surjective? Well, the reason it's going to be surjective is that all elements in the image of the homomorphism do have elements in the domain ring that are being mapped onto them. Okay? Otherwise they wouldn't be in the image of the homomorphism. Now, all elements of the domain ring are in a coset. Okay, so if you want, for instance, to know which coset is going to be mapped onto a certain element in the image of the homomorphism, so let's say you've got some element in the image of the homomorphism and you are questioning whether this element actually has a coset under this map that is mapped onto it, quite simply say, well, which element in the domain ring is mapped onto this by the ring homomorphism? There must be some element, okay? So, to draw a picture, here, let's say this is the element that's mapped onto that element by the ring homomorphism, and then just take the coset that contains that. That coset is now going to be mapped onto that element in the image of the homomorphism by my isomorphism F down here. Okay, so that's why I can argue that it's surjective, because the ring homomorphism is surjective onto the image of the homomorphism. Okay, now, injective then. Why is it going to be injective? Well, the reason it's going to be injective is because every single coset that is different, every distinct coset here is mapped onto a different element in the image of the homomorphism. We've shown that here. So, indeed, every element in the image of the homomorphism cannot have two cosets being mapped onto it. It can have one and only one coset being mapped onto it. So that's how we know that it's injective. So it is injective and it is surjective and it is well defined, therefore we have a beautiful bijective map. Now what we need to make sure of is that addition and multiplication are compatible between the two. Okay, so that this map preserves addition and multiplication. It truly is just a relabeling map that turns one ring into the other. Okay, so what do we need to show then? So we need to show that f of a bar, I won't do times first, I don't know what made me decide to say that, plus b bar is equal to f of a bar plus f of b bar, and some colour is going to be needed here to label up the different additions. Okay, so this addition here is addition in the quotient ring. Okay, so we're adding two cosets together in the quotient ring there, so I'll denote that in red. Whereas this addition here is in the image of the homomorphism, and as usual I'll denote that in purple. Okay, so we need to make sure that this is true no matter what a bar and what b bar you pick from the quotient ring. Okay, so how am I going to show this? Well, of course, addition in the quotient ring is defined in terms of addition in the domain ring. Okay, so let's firstly take the left-hand side here. If I want to add a bar to b bar, how do I do that in a quotient ring? Well, we've been studying this all video. You take an element from this coset, you take an element from this coset, add them together in the domain ring, and then take the coset that contains that. So we'll add a and b together in the domain ring, and then take the coset that contains that. Okay, so this addition will now be addition in the domain ring, so I'll colour that in orange there. Now, what is f of this coset then going to be? Well, any coset is mapped onto phi of a representative from that coset. Which representative are we going to take from this coset? Well, we might as well take the representative a plus b. Of course, you can take a different representative, but why on earth would you? Okay, we know that everything is well defined, so do not worry about what would happen if you took a different representative. Keep this simple. Use the most obvious representative possible. Okay, that will actually work nicely. So what we'll end up with here is phi of a plus b, and remember that addition is addition in the domain ring. Okay, so this is why this is all going to end up nice, because we know something about this. We know that we can expand that. Okay, so I've worked with the left-hand side here. Now let's work with the right-hand side. So f of a bar, well, just by definition, you take a representative from here and you take phi of that, and that's what f of a bar is going to be mapped onto by f. Okay, so this is just going to be phi of a. So we've just used a as our representative here. Again, why would you pick any other representative? You could pick another representative, but why would you? Okay, and f of b bar here, again, we'll use the representative b, will be sensible here. And then we'll put an addition in between them, and of course that addition is still addition in the codomain ring. Okay, or in the image of the homomorphism rather, because we got rid of the bits of the codomain ring that aren't involved in the ring homomorphism at all. Okay, and why are these two things equal to one another? Well, the reason is because that's the additive criterion that the ring homomorphism had to obey in the first place, that phi of a plus b had to equal phi of a plus phi of b, no matter what a and b you pick from the domain ring. So indeed, that is going to be true, and so effectively, the additive compatibility of this isomorphism here just boils down to the additive compatibility of the ring homomorphism. And indeed, multiplication is going to work in exactly the same way. So if we want to prove that f of a bar times b bar is equal to f of a bar times f of b bar, we're just going to apply the definition and reduce it into a statement in terms of the ring homomorphism in exactly the same way. So this is multiplication of the cosets, so this is multiplication in the quotient ring, and this is multiplication in the image of the homomorphism here, so we'll have it in purple. Okay, right, so again we'll take the left-hand side here. If we want to multiply a bar and b bar together in the quotient ring, we just take a representative from here and multiply it by a representative from here in the domain ring, so it'll become a times b, and then we take the coset of that, so it'll be a times b bar, okay, like so. If we want to ask what is f of that coset, so what will this bijective map, isomorphism to b, actually map this coset onto? Well, we take a representative from this coset and we take phi of that, so this will just be phi of a times b, again picking a nice, easy to work with representative. Okay, like so. Then if we work a little bit with the right hand side here, f of a bar, just by definition, of course, again, we take a representative from here, we'll use the representative a, so we take 5a, take a representative from b bar, we'll use b, and then we will have 5b here, and then we'll have these two multiplied together still in the image of the homomorphism here. And again, those two things are going to be exactly equal to one another because of multiplicative compatibility between the domain ring and the image of the homomorphism for the homomorphism here. So indeed, these two things are going to be equal to each other. So compatibility of multiplication for this isomorphism here boils down to compatibility of multiplication for the ring homomorphism. Okay, so indeed, that's all we need to prove. We've got that it's bijective, we've got that addition is compatible, that multiplication is compatible. Remember, for ring isomorphism, we don't need to bother checking that the multiplicative identity is mapped onto the multiplicative identity, because if you're dealing with a ring isomorphism, you can say that it's true that this thing implies that the multiplicative identity in the domain is carried on to the multiplicative identity in the codomain. Okay, we discussed that in more detail in the video on ring homomorphisms and ideals. Okay, so this is enough. We have now shown that these two are isomorphic. Okay, so to summarize then, what we have now got is a very nice understanding of ring homomorphisms. Okay, really what you are effectively doing, if you have a ring homomorphism between one ring and another, is you can think about partitioning up the domain ring into the cosets of the kernel of the homomorphism and mapping all of the elements in a coset of the kernel of the homomorphism onto a single element in the image of the homomorphism. And indeed, the multiplication in the image of the homomorphism and the addition in the image of the homomorphism will be completely isomorphic to the way that you'd have addition and multiplication defined on the cosets if you were to construct the quotient ring. So that now gives us a complete and utter understanding of how ring homomorphisms work in terms of quotient rings. Okay, and with that we'll finish this video.